So, model parameterization. Going to go down memory lane here. It's kind of cute, so I haven't changed it since a little bit. I've changed it this morning, but it kind of explains the equations in Ecopath and the concepts behind Ecopath. It's about mass balance, and I'm using the concept here of pies, not in pies in the sky, but pies in the sea. So when you have an area like this, when you have a fish like this represents this intermediate predators, whatever it is, some weird thing pre-photoshopped somehow into looking, well, intermediate predator of some kind. That circle there, that is to represent the consumption by that group. And that consumption we here break into three components. One is predation. One is production. Production incorporates then predation, catches, and other mortality. So this is what we get numbers for, at least the catches, the predation, other mortalities, maybe not. That's the production for the group. And then we add to that respiration and E there, E for egestion or excretion. So this is what we do for all the groups. We split consumption into production plus respiration plus unassimilated food. And in general, we would say production is something like 10 to 30% of the consumption of this pie. Unassimilated food is typically around 20%. And respiration would then be of the order of half of the energy. Respiration is the work that a group has to do in order to do all the metabolic work, keep things going. It's higher for marine mammals, it's lower for things that move slower, or for bacteria or small things. But the general thing is we split the consumption pie into this, and this is actually the first of the equations that we'll be talking about in the next slides. We do this for all the groups. So we do it for this group. We also do it for these small pelagics. We also do it for the benthos that we see down there. We split them into, we look at of the consumption, how do we break it into proportion. So that's one important part of getting going on establishing a food web with all the linkages and biomass that go into it. Now the next thing is, what do they eat? So in Ecopath we also give a diet composition. In this case here, roughly you can see that this intermediate predator eats 60% or so from here. That's the size of this pie here, which is part of the small pelagic pie, consumption pie. And then they maybe eat something like 40% of benthos. This is what you see down here. So when we know how big the pie is for the intermediate predator over on the left, and we know the diet composition, that means we also know something about what's on the right side there, on the prey side. We know the demand by the predators. And if we do this for all the groups in the system, we are getting information, we're using information about the consumption by the predator to inform us about how much is being eaten of the prey. We are also, because we know or estimate the size of the pie, consumption pie, for the small pelagics and for the benthos in this case, we also know something about how much is possible. And it has to match. So we're using information about the predator's consumption to tell us something about demand on prey. And we're using information about prey production to tell us something about possible consumption by the predators. And that's what we try to make, that's what we have to make matching. We have to get that to match when we set up the overall food web. So, just one thing more about this slide is how big are the pie? Like this funny group chord thing there on the left. The size of the pie here. Well, we can estimate that if you think about it from how big the biomass is times how much does it consume by unit biomass. We call that biomass times Q over B, consumption over biomass ratio. So that will tell us something. The biomass times its consumption rate tells us how big each pie is. So that's basically all there is to Ecopath. You know, that's it. That's all what you see here. There are some small things in addition to this, but this is basically it. These are the two equations you see here. If you think about it, at least you can see the two equations. And yeah, that's it. We can stop now. I can see in my corner Santiago is smiling away somewhere. Anyway, yeah, this is it. And for the rest of the time, we're just going to be discussing it in a little bit more detail. But really, this is it. This is all there is to it. This is Ecopath in a nutshell. No, this is Ecopath in a pie in the sea. That's it. So let's look at the equations. The first one is what we call master equation number, either 1 or 2. I keep changing the numbers. But it says consumption equals production plus respiration plus unassimilated food. That's what you saw before. That's this breakdown of this one here. We break it down into production, which is this part, plus respiration, which is about half of it, plus digestion or unassimilated food, which is about 20%. So that's the first equation. The next one is how we break down the production part of it. And for that, we're using 5 terms. There's the predation mortality that we talked about in the previous slide, 2 previous slides. So predation mortality plus fishing mortality plus biomass accumulation. Biomass accumulation basically means the size of the pie can change during the time we look at it. It's not steady state Ecopath, it's static. It has no time component, but it looks at what happened in a year. So if a group is being overfished, there will be a negative biomass accumulation. If it's recovering after overfishing or because of good conditions, it's increasing, that's a positive term. Then there's net migration, because all ecosystems are connected. There's no isolated ecosystem on Earth. Well, not even the Earth is isolated. Think about how much comes into the Earth every day from outside. So there isn't any, there's always interaction with neighbors. That's why there's net migration, things move in, things move out. Net meaning difference between in and out. And then there's the unexplained mortality, the other mortality. That's the one we don't have numbers for. So we break down production here in the second Ecopath mass equation into predation mortality plus fishing mortality plus biomass accumulation plus net migration plus other mortality. I'm just about to say it again because it's almost like a mantra. We keep saying that over and over again because when you work with it, this is what you have to get into your head, that we have these things to play with. We can express it, as you see down the bottom there in an equation. And if we do that, we are actually going to get one equation for every group in the system. If you're not used to it, oh, it looks pretty complicated, doesn't it? But then you look at it, and you basically, these are the terms you see down there for what we are working with as input parameters or estimated parameters in Ecopath. So it's all there. It doesn't get much more complicated than what you see here. It says first P over B times B. P over B is production biomass ratio, which corresponds to the mortality rate, total mortality rate for a group, times B. If you multiply those together, you get P. That's production. We don't enter production directly. We enter this ratio, P over B times B. B because we can measure the biomass in a system or get estimates on the biomass in a system from assessments or from somewhere else, but typically from assessments or even from guesses. P over B, the total mortality rate, that's what is estimated in assessments again, and it's something we have expectations for that. But you ask me what's the production of herring in the North Sea, and I would have to think pretty carefully about to figure that out. From, I think there are about 800,000 tons, and they are probably turning over 0.5 times per year. So I would say it's about 400,000. You know, you have to get into that. Whereas P over B times B, these are estimates that's much easier to relate to. So we tend to use that kind of ratios. So again, production is on the left side, and on the right side is how we break production down. So the first term there is predation mortality. That's something with Q over B, that's how much is being consumed by a predator. Consumption biomass ratio for a predator, J is the predator, times how many predators are there. And DC just means what's the diet composition for this predator for the prey I that we are interested in. So we sum that up in the first term down there. We sum this up over all predators. How much they eat per relative to biomass times the diet composition. So straightforward. This is the predation that you see there. We add to that E, which would be the net migration, in this case here. We add the catches, and then the biomass accumulation. That's the term for do they get bigger or smaller. And the last complicated term is really just the other mortality. It's introducing this EE that we'll be talking about in the future, which is, or in the next slides, which is ecotrophic efficiency. We'll get back to that, but this last part is just the other mortality. So that's our two equations. Marta summarized them like this, and I won't mention them again, but again, there are just those two. What happens to consumption? Consumption equals production plus respiration plus unassimilated food. I am mentioning them again, sorry, I said I wouldn't. But again, these are the only two equations you have to worry about to get a grasp on Ecopath. So consumption equals production plus respiration plus unassimilated food. And the second one is we break down production. We break it down into predation plus fishing mortality plus, I've done this too many times. We break down production into predation plus fishing mortality plus net migration plus biomass accumulation plus other mortality. Arrangement is slightly different there. You can see though on the lower left here. This here is the consumption, the blue here in the background, and the consumption is broken once again into production plus respiration plus unassimilated food. You know it by now. And then the production part of it is split as this one here. We split that into predation plus fishery plus net migration. Biomass accumulation is not mentioned here, but other mortality is. Biomass is not mentioned here because that's how big the consumption pie grows. So that's it. As I mentioned, for the second equation here, the one about production breakdown, that one we can split into we can make one of those for each group in the ecosystem. And you have that here in the lower right. You see this terrible long line equation here. And it's terribly long because there are these dot, 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 because in this equation, if you have 50 groups in the system, you can set up 50 equations, and they will each have more than 50 terms in them. So it's quite a bit of a set of linear equations. But you may remember about linear equations that when you have such a set of linear equations, you can estimate one parameter for each equation that you have. So if you have a group or an ecosystem model with 50 groups in it, it means you can estimate 50 parameters, one for each line that you have. And it's not just a question of that you can do it. It's really that you basically have to do it. And have to do it because there may be inconsistencies in these set of linear equations. It's not so that all the numbers match. It's not like fixed numbers that we put in there like we did to solve equations back once upon a time. No, there are inconsistencies in these estimates, so they don't match perfectly. Now, because of that, what we tend to do, or what we do, is we estimate one parameter for each group in the ecosystem. It can be any of the basic input parameters, and the basic input parameters are, we can go back and we can look at them here. That was in the lower right picture here. There is a biomass, a production biomass ratio, a consumption biomass ratio, so biomass, production consumption, consumption biomass, or I skip down here to ecotrophic efficiency, which is the production used in the system. That's the term you saw before up there. So we have those four input parameters. As you can see here, one less the this production used in the system. Production used actually means production that we describe with the model what happens to it. That's our ecotrophic efficiency. 1 minus EE is the unexplained mortality or other mortality, the things we don't explain in it. Now, we have those four. And the rule is basically estimate ecotrophic efficiency if you can. If you have an estimate for biomass, estimate ecotrophic efficiency. You can estimate that, or QB, or consumption biomass ratio for a given group. This is all by group. Or production biomass ratio, total mortality. That's the third option here, or biomass. However, forget about estimating PB and QB. We have estimates. We know what they should be. We don't know what the biomass is. We don't know what the ecotrophic efficiency is. Those are the two ones to estimate. Ideally, you would have estimates from assessments or from surveys or from other means for the biomass. Then you can get PB and QB, and you estimate the ecotrophic efficiency. That one is other mortality there, or rather, how much your model explains of the mortality in the system is really difficult to estimate. We can have expectations for it, but estimating it, and we may have to guess it if we don't have a biomass. But think of it as it's either biomass or ecotrophic efficiency. The rest you can get. Fair enough? Good. Now, so much for the input parameters. This is basically what you need to construct the model. Then what goes into the model? Well, we typically talk about functional groups for that. And a functional group, that can represent a group of species, it can be a single species, and can even be a life stage. We have the option, of representing a functional group being the unit, that's what's on each line, that's what makes each equation when we set up that set of linear equations that you don't really have to worry about, just what I said before. But these functional groups, meaning the things we put in the spreadsheet, in the interface, they can be either a biomass pool, or they can also be what we call multi-stanza group. So that could be you have eggs and larvae, you have small juveniles, you have larger juveniles, you have 1-year-old, 2-year-old, 3-year-old, 4-year-old, as detailed as you want it. Now when you do that, with that set it up with this multi-stanza, it's an age-structured model where we keep track of numbers by age and see how they basically build population dynamic models within EWE that keeps track of what happens throughout a life history of such a group. And that's useful when you have fishing only. It's useful when you have questions where it's necessary. If the resource questions you have don't ask for it, you probably don't need it. And you can do the simple biomass pools. The biomass pools are much simpler to work with, and the assumptions are much simpler. And remember, the best model is always the simplest model. Those you have a group, and you know they produce a certain amount every year depending on the conditions. That's what it boils down to. But we'll talk more about this. For the multi-stanza groups, you need a bit more information. I don't really want to go into details about that now. We'll be looking at that once we get further into it. But you basically build the population dynamics models based on what you see here. So you see here you have, in this case here, it's rainbow trout LRBT, and you have 3 stages here, 0 to 2, 3 to 5, and 6 plus, which builds down to something that you define when you set up the model, which is these start at 0 months, and then after 3 years, 36 months, they graduate to this group, and after 6 years, 72 months, they graduate to this group. So we keep track of what happens to them. And keep track of what happens to them, that's something that depends on the mortality. So here you define, okay, for the first group, the mortality rate, total mortality rate, instantaneous rate is 1 per year, and 0.7 and 0.8, that's the turnover rate. And when we have that information, we can go up here, and we have this here where we have age in month on the x-axis of this plot. And what you see here on the red line is survivorship. So we start with 1 relative unit, and then we look at, in the first 3 every month we estimate how many survives, and you can see here not many survives up to become 6 years old and to get to spawning. There's also here, you define something about, let's see what else is there. The growth. The growth is based on von Bertalanffy growth, which is basically everything does that. It works, it just works. So for that you need this curvature parameter k, 0.3, up here by default. You have to find that in FishBase or somewhere. And that's what defines the blue line here. That's the individual weight with whatever units are needed for that. But when you take the red line and the blue line and you multiply them together, so number times individual weight, you get the population biomass. And that's what you see here in the black line, going up and down again. It peaks here after a couple of years. The green lines here are the separation, and this here is where they reach spawning age. But you can actually overwrite that by spawning proportion. So it's a very simple way of setting up population dynamics model inside EWE, and there's a bit more to it. We will be talking more about it when we talk about especially when we talk about the time dynamic simulations a little bit later. It's there, I want to mention it. You use it when you have reason to do it. And so it's a research question that depends on whether you use this more complicated model. If you do, it's really quick to set it up. Enough about that. You will be needing a lot of information for this. Ecopath is, I like to call it a gourmet, in the sense that, well, a gourmet more than is, we have this garbage in, garbage out concept, you know, that if you feed a model with bad data, you get a bad output out of it. That goes for any model. And models like data. So that's why I talk about gourmet in the sense that if you feed good information, you get also something good back. You give it to a good chef and he will produce really nice food if you give good ingredients, if you have good ingredients, and data is your ingredients. What they do is basically limit the possibilities for what the model can come back and tell you. The better data you put in, the more constraints you're giving the model. And all models like that. It makes it more difficult, but it's a much more constrained output that comes from it. Beth kind of talked about that in her talk last week, when she was asked about how many Atlantis applications there were, and she said, well, it's not like Ecopath where you have one for Europa. Now, I trust you all know what Europa is, but just in case, it's not the place where the European Union is. It's actually the fifth moon of Saturn, where there may be ice on the surface, and possibly there's liquid of some kind under the ice. Someone published a model in astrobiology. Yes, there is a journal called Astrobiology. About 15 years ago. It's in the Ecopath collection, my Ecopath collection, that you hopefully have access to. If not, send me an email or go to the Slack channel. You can find the link there. 1,000 publications or so. Now, so this describes life, a food web model for life under the ice on Europa, on the fifth moon of Saturn, where we don't even know if there's water or whatever it is underneath that ice, if there is ice. So that's probably one of the easiest models to build because there are no constraints, only general relationships. Constraints makes it more difficult, and that's what this slide is about. It's about pedigree, which I also have to explain because I had no idea what pedigree was. I maybe a little bit when I first heard the term, and I'm not English speaking, as you can hear, and so are only a few of those on this call native English speakers. Pedigrees is something a horse has or a dog. It basically means you know where it comes from. You know its parents, its grandparents. So these are the track horses that run for big sums, or dogs that have the same. You know the history of them. We use this concept to talk about data as well. So we're talking about where does this data come from, and we use this to characterize the uncertainty in the data. So we assign a pedigree index, and we have a structured way of doing it. So you can see on this slide here, which happens to be for consumption biomass, it can be estimated by Ecopath, which basically means it has no pedigree, it doesn't have any history and so on. Guesstimate, so a guessed estimate, that's better. From another model, a little bit more, and then goes on up to same system. So it really is based on data for that species in that system, and I think the last part on that line is high precision. You can see down in the bottom for biomass. It's estimated by Ecopath from other model guesstimates. I'm talking about down here. Approximate or indirect method, sampling locally with low precision, sampling locally with high precision. That gives us a ranking for it. And we assign an index to that so that we can estimate what's the pedigree overall for this model. And we also assign a confidence interval to it. And you can say, of course, well, where did you get that from? Well, we just made it many years ago. And the nice thing about this is that it's not crazy, and it helps you a lot get it through publications and so on. That you can always blame us for. You can always, this is the default values. They're pretty good. And the whole thing, the nice thing about this way, that if you add this pedigree to your data is, first of all, it gives you an overview. See, they're up there in the top right, how you get an overview just by looking at the colors here. The darker the colors or more red, sorry for the colorblind, we really should use, we are, there's a different story, but we are actually being much more considerate of that. But it's an old slide. You can see from this how well rooted this model is in data. So that tells you something. Even more importantly, when you talk about the model and you present it to someone, you can in one slide say something about how much we know about the data or about the ecosystem and information in that ecosystem, how well it's rooted in data. That's what you can get from this. Now, remember, if you don't have much data, that's not your problem as a modeler. You're the one digging it up. You're the archaeologist digging things out of the ground when you work with this. So you're the one giving the overview. Don't be shy or sorry that, oh, I don't have data. Well, there's always data, and this gives an overview about it. In addition to this, because of the structure there where we assign uncertainty to it based on what type of parameters are, that's a well-defined method, and it really makes it easier to one, get it through publications, and importantly, gives you a structured way of handling uncertainty at the system level. So what we're trying to do is, with Ecopath, build one model that is possible, and then we throw the uncertainty book at it afterwards. This here is a big, well-structured way, big help and a well-structured way of doing it. That's what you get out of this. So much for that. Now, I have been through 10 slides now, and I've been talking way too long. And we still have 16 to go in this presentation. I'm not going to go through the details of it. I'm just going, for the rest of this presentation part here, I'm just going to talk a little bit general about it and then leave it to you to read through the presentation and come back with questions later on. And again, you can do it in Slack, you can do it by email, or you can get hold of us otherwise. But when you have specific questions. So biomasses is first. Getting biomasses is really good. If you can dig for them. Biomasses don't travel well, meaning that if you're working in one bay, you can't necessarily just take the biomass and exploit this fish species from another bay where there might be totally different fishing pressure and feeding conditions and so on. You may be able to do that if it's comparable and if it's unexploited groups, or if it's but generally you can't do it. But you have to be really careful about it when it doesn't travel well. POB, we have a lot of information. That's the total mortality rate. That's what you get from assessments. The one thing I want to emphasize about turnover rate is if you invert it, again, the unit, because units are important, the unit is per year for P over B. But if you invert it, so you take biomass over production, you get the average longevity, and it has a unit of year. So that number tells you how long time does an average animal live in my system. So in tutorial 1, marine mammals had a P or B value of 0.05. If you invert 1 over 0.05, if you invert 0.05, you get 20 years. So the average marine mammal in our model lives 20 years. You can relate to that. If you're not used to it, 0.05 may not tell you much, but 20 years, you can think about, is that reasonable? Well, if it's anchovy and its average lifespan is 20 years, you would know, something is wrong. Or if it's seals and the average longevity is a month, something would be wrong. And always think about it from that perspective. Just look it around. Then you have a way of handling it. There are ways of getting it. You can read about that. You can go to FishBase. We'll hear more about FishBase next week from Deng Palomares. Q or B are relatively easy to get, and what you really have to think about is the ratio between production and consumption. I talked about in my pies in the sea charts up in the beginning. I talked about how we have the consumption pie, and we split it into production and respiration and then unassimilated food. Well, basically there, production is for fish 10 to 30% the consumption. That means production-consumption ratio is 0.1 to 0.3. So it also means if you can get the mortality rate, or guess it from average lifespan or something else, lots of methods, you know what the consumption is just about. So don't estimate it. Don't let Ecopath estimate it. Just to say, don't throw away a shot like that. You have better ways of getting it, including from the tail story of Dan and Deng Palomares. She did her dissertation on this actually. So that's next week. Empirical relationships are good, and you can, for invertebrates, you can get estimates from there. And I talked about production consumption. Typically it varies between 0.05 and 0.3. That's the pie, how much of the pie is being turned into production. It can be lower if it's really talking about, when we're talking about whales, when we're talking about birds, it's lower typically, it's lower. And if we're talking about very small things, fast turnovers like bacteria, it can be up to 0.5. But they always have to be a good part of the consumption going to respiration, because that's the work we do. That's all organisms have to, metabolism that takes part of the consumption. Finally, ecotrophic efficiency here, not finally, but next. The way we estimate that is in the first equation. It is how much of the production does the model explain. And that's the 4 out of the 5 terms in the production equation, which I hope you remember by now. You remember production equals predation plus fishing plus biomass accumulation plus net migration plus other mortality. Oh, and that's what's missing here in the top of this equation. See the 4 terms? Other mortality is missing. Divided by production. If it had been there, this equation would be 1. So ecotrophic efficiency is the proportion of production that the model describe what happens to, that you explain with your model. That's it. So you sum these 4 terms up and divide it by production, and you get the ecotrophic efficiency, which means 1 minus ecotrophic efficiency is the other mortality. And if you can, let Ecopath estimate that. It's often close to 1. For things that are being eaten, I say small pelagics don't die of old age, they are typically eaten or fished. Phytoplankton, when you have blooms in the system, we find like seasonal blooms, typically those systems, EE is down to around 0.5 for the groups. If it's really clear water like coral reef, the EE of phytoplankton has to be close to 1, because phytoplankton is being eaten in those systems. That's why the water is clear. There's still high productivity, but really fast turnover. Yeah. Diets, we can get them. There's a lot in FishBase. There's a lot. It's been studied for 100 years. We know a lot about diet, and don't despair if you can't find a diet for a group in your model and so on. You just can't find it. What you have to remember is your research question. Then you can look at how sensitive that research question is to uncertainty about this, but don't stop because of this. Just carry on, and typically it's not a big deal to find numbers for this. Yeah, that's about it. There are a few other things which I don't want to talk about. I talk too much now. So let's go. No, you have to work your way through this, and I don't want to feed you too much, but at the higher level, for living groups, the biomass accumulation rate is what tells the model if the biomass in that static situation that you describe with your Ecopath model is a steady state, then biomass accumulation rate is 0 for a group, or is a group increasing or decreasing, then you have a biomass accumulation rate going one way or the other. It's important when you go to the time dynamic models later on, because if you have a biomass accumulation rate, like in tutorial 1 we had marine mammals increasing with I think 2% per year or whatever it was. That is being carried over to a time dynamic model that says, that's being told that under the conditions of your Ecopath model, it was not steady state, but there was this increase. So it knows that under these conditions, biomass was going up or down, I suppose, for seals because of harvesting, and it will put things on a trajectory. We'll talk more about that with the time dynamic model, but that's what this is important for. There's the detritus group. We need to know for each group how much is being sent, what happens to detritus. We need to define that. And for fishery, the Ecopath was originally designed to look at fishery effects from the very beginning. So there is a lot of ways of handling fisheries throughout the system. If you think about it, it's likely that it's covered in there seriously. So we can deal with landing, we can deal with discards, we can deal with what happened for it. There's been a lot of studies on discard fate, as I'll talk about briefly on Thursday. But there's a really good way of handling that, and that goes for economic part as well, as Santiago will be talking about later. So, enough about that. I talked about biomass accumulation. Non-assimilated food, typically about 20% for fish, and it's the term here in the master equation. The master equation number 1 says consumption equals production plus respiration plus unassimilated food. In case you haven't heard it before, get it? Yeah. Migration. There's immigration and immigration. That deals with things that move over the borders. And we need to put enter information about that. We can also deal with seasonal migration in ecospace, but that's later. China trade we talked about, cost of fishing, don't want to talk about market price. And I see now that this is the end. Good, we're done with this first part of the talk. Yeah, are you ready? Good. What I intend to do is something quite different. I'm going to go to YouTube. I recently was in here and I looked for just to see what was there on Ecopath, and I found a small video here, 6-minute video that gives a summary of what I've just been talking about for a year, and it's from a project down at the University of New South Wales, where they made with several of the students. You see 3 here. Ecopath models explained, the Coll Reef case study, this one about how does Ecopath do it. Ecopath explained examples and everything, and a few other ones. I thought it would be interesting to show you this one here.
Imagine a single fish. For just this single organism, it can
Yes.
be relatively easy to determine the requirements that shape its weight, diet and lifespan, and determine the biomass of its species population as a whole within a certain area. But no fish exists as a single discrete unit. They are instead parts of a much larger ecosystem. All organisms that interact with this fish, whether in terms of predation or prey, also have a specific set of requirements that dictate their biomass. How can we determine the biomass requirements for every species within an ecosystem, and the ways this biomass moves between different species through processes of production and consumption? The answer lies in Ecopath. The Ecopath programs create a model which represents a static, mass-balanced snapshot of the resources in an ecosystem and their interactions, represented by trophically linked biomass pools. Now this is quite complex, so let's break it down a bit. A model is a consistent description, in this case of the resources or biomass within an ecosystem. These can take the forms of text, graphs, or equations describing states and rates. A static mass-balanced snapshot refers to the fact that the model is describing the ecosystem not over time and space, but in a single moment of time, accounting for all material entering and leaving the system, whether this be via migration or mortality. In terms of resources, interactions, and biomass pools, within the Ecopath model, resources are represented as biomass pools. These pools are defined as species groupings, meaning that the resources and their interactions can be understood as the movement of biomass throughout the ecosystem. So, in other words, Ecopath gives us a consistent description of how the biomass of certain species groups and how this biomass moves within and between species groups at a single point in time. This model can thereby tell us the biomass budget for an ecosystem, which is the difference between the production and loss of biomass within an ecosystem. Ecopath acts under the assumption that the ecosystem exists under equilibrium conditions. This means that the ecosystem is existing in a balanced state that keeps population size within a sustainable range, with enough species existing at each trophic level to sustain the entire ecosystem. If an ecosystem is balanced, biomass produced and lost are equal, meaning production minus loss equals 0. Therefore, Ecopath can tell us exactly how much biomass production and loss is needed within species groups in order for an ecosystem to maintain an equilibrium state, and can thereby allow us to estimate unknown biomass of a certain species group that would be expected in a balanced ecosystem. Before attempting to model the biomass in an ecosystem using Ecopath, you need to define the biomass pools, or species groups, that you will be applying the model to. The organisms within these groupings should share a trophic level and hold similar life history traits, such as reproductive behaviour, life stages and lifespan, and similar population parameters, means a similar mean and standard deviation population size. As long as they share these factors, the level of specificity is up to the user, with more restrictive groupings giving more detailed model output, whilst more aggregated groupings will give broader outputs. Once these are defined, Ecopath calculates the annual production and consumption of each species group with two master formulas. For each species, production can be calculated via production equals catch plus predation plus migration plus biomass accumulation plus non-predatory biomass mortality. And consumption can be calculated by consumption equals production plus respiration plus unassimilated food. In order to fill in these formulas, there are 6 major parameters that Ecopath needs to know for each of the species groups: biomass, total mortality or production to biomass ratio, PB, consumption to biomass ratio, diet composition, fisheries harvest, and ecotrophic efficiency. Let's break these down a little more to understand them. Biomass is defined as the total quantity or weight of organisms in a given area or volume, and is relatively easy to measure in grams per metre squared. Total mortality is related to production in terms of how fast a species group grows and dies. For most fish groups, where growth rates follow a von Bertalanffy phi curve, and mortality rates are negative exponential, their total mortality is derived from fishing mortality and natural mortality. For primary and secondary producers in these ecosystems, whose growth is more likely to be linear, their P/B ratio can be calculated as the reciprocal of their mean age. Consumption to biomass refers to how much species groups eat and how much they are eaten. Ectotherms usually have a lower Q/B ratio than endotherms, and can be estimated via oxygen consumption or using the aspect ratio of the tail. For both P to B and Q to B ratios, literature is often referenced to get general species group estimates. Diet composition refers to what species groups are eating, given as a fraction by weight of the species group it consumes. It can either be generally assumed from trophic level or determined from gut content analysis. Fisheries harvest only applies to groups that have substantial fisheries mortality from catches, discards and poaching, and can be obtained from fisheries data. Ecotrophic efficiency refers to the proportion of production that's actually used in the system, or the remaining mortality as a proportion of total mortality. Since almost no system is truly closed, with production lost via migration, fishing or predation that brings the biomass outside of the ecosystem studied, this value helps to balance the lack of precision in all other calculations. Even if Ecopath is missing some of these parameters for some species groups, it runs simultaneous linear equations to find estimates of the values for these groups and gives a rough output model that represents the flow of resources throughout the food web. These models can highlight areas of the ecosystem that require further research, or suggest expected biomass values for a balanced ecosystem that can be compared to those calculated. It brings together the work of many varied fields of research to shed light on ecosystem dynamics, aiding in policy making and management processes to help keep these systems in a balanced state.
So that was made by Indy Riley, a student at University of New South Wales, and I think the task they had was to do it in 7 minutes, so or 6 or 7 minutes. So it's quite quick, but I think it gives a nice overview of basically what we just been talking about for the last hour. So you put together a model, you got the data in there, and the next thing is you do the parameter estimation, and the model comes back screaming at you because it's not balanced. So what do you do then? That is what we'll be talking about here in the next little while. The procedures that are involved in getting your model balanced, because this is the next step. And remember, what we're trying to do now is not to estimate the model of the food web in the ecosystem that you're working with. It's to make a possible model. That's the ambition level. That is what should be the ambition level for your work. Not the ultimate model. It's not the masterpiece. It's one possible model that you are developing with whatever information you can find that is relevant. You focus on your research question and you make a model to look at that. Once you have that model, we can really, as I mentioned before, throw uncertainty at it. Lots of methods for that. But you need to get past this first hurdle. And I have a few things in the presentation here I'm not going to go through, as such as about the background for it. I'll point that out here. But the key there is we are using information about the predators to tell us something about the prey. It's all the different mass balances here that we keep track of with that in mind. It's the pie in the sea where predators tell us about the prey and vice versa. Now when you put that together, this picture here, the pies in the sky, you do that based on information about, say, a predator, like the one on the left here, and its diet composition. So you do it from the eyes of the diet composition. Here's another way of looking at that, because what we're talking about is we're talking about two-way ecological bookkeeping. That's what Ecopath does. So when you make your model, you do it from the predator's point of view. You say for a given predator, what's the diet composition of that? It's this much and it's this much. So this is what you put in your input data, which result in a consumption by that predator which is this big. And you do that for each of the predators. You define the diet composition. all the way down, and that results in some consumption rates, and this is how much they consume. When you press the mass balance parameter estimation in Ecopath, what Ecopath does then is it estimates for each group in the system, including those up here because they are both predators and their groups in the system, but here it's illustrated for some prey groups. It calculates for the prey groups how much do the different predators need and sums that up. And now it looks at this production thing over here, how that compares to what is the total production possible for that group. And it needs to balance this. So when you construct the model, you're looking at it from the predator's point of view. When you balance it, it's from the prey's point of view. It has to match. There has to be enough production to feed the predators and the fisheries and all the other demands on it, all the constraints that we add to it. That's what we're trying to do. And the model comes back and screams at you. Ecopath or ecotrophy efficiency is bigger than 1, or respiration cannot be negative. Well, those two messages are the typical ones. The first one means that you have too much demand on productivity for a group. Consumption times biomass times diet composition for the predators is summed up. What they take of this prey is more than the PB times B for that group. So that's the first of this type. The other type, respiration cannot be negative, comes from the other master equation, the first one. Consumption equals production plus respiration plus unassimilated food. We estimate consumption, production, and unassimilated food. So you can see in that equation, what we do is we turn it around and we say respiration equals consumption minus production minus unassimilated food. If that's negative, well, that means production is probably bigger than consumption. So that's what you need to go back and look at. It's fair enough. But what was it? Well, when we look at Ecopath, and I'm going to open Ecopath in a few minutes, and then you'll see a status. So you actually can see where it is. If you are sitting at the screen, if you go down in the lower left, second thing down there, one of those two down in the lower left is called status. That's where you have all the messages about what's happened behind the screen, what Ecopath is doing. Yeah. So to get mass balance, you go to Ecopath output basic estimates, and all the EEs should be bigger than 1. Again, ecotrophy efficiency tells me how much of the production that's used in the system. And used meaning, as we talked about just before the break, that it's this equation here about, oh, there we are, predation plus fishing plus biomass accumulation plus net migration divided by production. So 4 of the 5 production terms in the second master equation divided by the production. That's our ecotrophy efficiency. Nothing magic about it. It's really just a net convention there of everything but unexplained mortality. Now, it is feasible to find, to mass balance the model. I was scolded years ago by saying I had never seen a model that couldn't be mass balanced in 20 minutes. Scolded by someone reminding me that, yeah, maybe you can do it because you tried a number of times. And that does help. But there are some procedures and some steps involved. So what I found is if I sit down with someone who knows the data, we can talk our way through what needs to be done fairly quickly. Just by the one who knows the data also knows, oh, I don't like changing that. We're quite certain about this, but this I'm uncertain about. And that's the kind of thinking that goes into it. And then there are some steps involved, and I'm going to take you through some of those steps, some of those procedures in this hour here that we're in now. But as a rule, they start with a bigger problem, because the bigger problems are, in this case here, often the easiest ones to solve. Where it gets really difficult is when you get down to, oh, my EE is 1.1 and I don't want to change this data. Well, you have to find a way around this. And then you could be smart and think, well, do I really have to? Couldn't you automate that? Finding a way of doing it that's smarter than I am. Some artificial intelligence, maybe? Been there, done that, dismissed that. There is a paper somewhere by Pat Kavanagh, who worked with us on this, and Pat Kavanagh was smart, is smart, she's still around. What she did was, so we have this, we have all the input data, and let's find a smart way of tracking and making a balanced model. The problem with that is, what's here at the bottom, what if there are data conversion errors? If we do that, we're producing garbage in, garbage out. And that's what happened with that method. And you see, when you're putting together a model, let's just be polite, not too ambitious and say we have 20 groups in the model. We have models now with several hundred, but that's a different story. Just 20 groups. That means you're putting in 4 input parameters for each, and diet compositions and catches. So let's just say that it's 4, 5, 6 times 20, 120 parameters. Now, what's your error rate, do you think, when you're making, for these you have to make conversions, and you have to estimate this and this. There's a lot of spreadsheet work that goes into making a model. You make mistakes. Everyone makes mistakes. So, out of the 120, let's guess that there are 2 conversion errors, or 3 conversion errors, or 4. It's that kind of numbers we're talking about. Now, an automated routine has to be very, very, very smart to find that. It actually might be possible to do it, to set something up that knows all the rules that you need to do it. So yeah, if you got that into it, it could be automated. But what we're doing there is looking for finding errors, and errors pop up if you start looking for them. That's when you get in that the biomass is 100 times too high and that kind of things, where typically conversion errors are orders of magnitude off, and they are the easy ones to find. But you take something which has a conversion error of that kind, put it into an automated routine, it has to be really, really smart to pick that up. So it's good to have that sense for how to do that. We covered this pretty well, but the procedure, which I'm going to explain, is you figure out what the problem is, and then you go through a number of steps. You look at the equation there. Now you figure out, is it predation or fishing? That's mainly is due to. If it's fishing, you go and check your landing. If it's predators, you check who are the important predators, and you check those ones. And one thing that's worth noting that we see in many, many cases is that a small diet contribution for a common predator can cause a high predation mortality for a rare prey. We see that now with salmon survival here in the Strait of Georgia, where seals take a tiny bit of the diet being salmon. It has a big overall effect. But another place where you see it commonly is if you have squid in your diet composition. If they take a little bit of a fish species, because squid are so common, that ends up being a huge consumption. So one has to be especially careful with cases where a small part of the diet for a common predator causes this big predation mortality. Sometimes you're talking about, oh, we can't have 1%, we have to go down to 0.8% or 0.5% or something like that of the diet, or I've seen even smaller cases like this. Actually, it led to a principle that I call the fixed selectivity principle, which is a useful thing when you're defining the model. So this is not balancing the model. This is a trick to avoid a common problem that we see when balancing it. And that is this. Here, the example I'm giving is, we have a predator that eats 40% small fish. Often diet compositions are to that level that they eat fish, small fish. Now, what is it? Many would just say, oh, we've got simple assumption would be we have 4 groups of small fish, so there's 10% each. But they are not all equal. Not all small fish are created equal. It's not Orwellian at all. Some are more equal than others, or some are more common than others, rather. So this principle is just, what you do is you figure out what is the production of those 4 groups. And you can say it's a better assumption that the prey is taken based on how common they are in the ecosystem. And that's production that matters there. It's not biomass. It's turnover rates matters too. That's how they make themselves available. Biomass is something that matters in the moment, but over the course of a year, it's production that matters. So that's what we have to think about. So you estimate that total production, and I can't help, I put that in last night using latex, and I hate latex, but that was an experience. I shouldn't say that. Now, it's the first time I tried it. That's why I'm saying using latex. And normally I don't. Nothing to do with what I'm talking about. But the principle is you estimate for those where you have this question like small fish, you estimate production of potential prey, and then you distribute based on that. That's a reasonable assumption, and reasonable means assumptions are the ones that pass through reviewers. So it's an important aspect, and through advisors as well if you're a student. When it's reasonable, that is usually the things that get you past. And it gets you past mass balance much, much easier. I've been working on complicated models where we use this principle and stuck to it. It's because it actually seems to work. Now, one thing you'll have to deal with, what do you change? There's some listings here. The principle in this, the more uncertain it is, the more you can feel free to change it. So this is another good example. Many of you will, when you're working on defining a model, be asking, relying on the research of many other people and getting an idea from them about how reliable they are. That information is great. In lieu of that, you can actually, just from defining the pedigree, get a pretty good picture of it, because some cases you will have to go to other systems or other groups or other, pedigree is a good way of handling that. So the lower the pedigree, the less the data is derived from local data, the more flexibility you have for changing things. So again, pedigree is pretty neat one to have as a background when you're doing the changes, and you will have to do it. That you can expect that you have to change some things. Some people keep track of that and put that into an appendix for instance, supplementary material. What was done? What was necessary to change it? What was the problems? Because it actually feeds back and talks something about data problems as well. So this is not an awful process, but actually there's a lot of interesting aspects to the mass balancing. Even if it can be daunting when you're not used to it, it's still the case. So What to check once a model is balanced? There are more things you can check afterwards. Pre-bal is one of them, and pre-bal is routine that, I'll swap some slides coming next, but it's one that Jason Link, who you'll hear on Thursday talk about it. Jason Link is, I'll introduce him later, but Jason makes a routine of what you need to look for as you are developing a model and you evaluate that model. To me, it's a post-balancing rather than pre-balance, but that's, no, it's pre-bal in the sense that you're not done until you have looked at does it make sense. So that's why I say once a model is balanced, once you have something that's balanced, you can start looking at these things, but you have to get to that point. That's a bit complicated. In doing so, I just put a reference here to FAO has some technical guidelines for ecosystem modeling. It's the report is on the web and it's in my shared folder. Careful design and so on. I won't talk about that. I also want to mention, though, that there is a paper by Sheila Heymans and others about best practices for EWE. Also worth, if you haven't read them, please do read them. There's one by Cam Ainsworth about 10 common mistakes that cover, again, some things that's worth getting into your head and reading. And then there's the pre-bal, which is basically think critically about your input data before you balance the model, before you finish off in this balancing. And what's in here is just common sense rules of thumb about how things should do. They can help you if you have pick out things which are gross errors in the model. They are really just there to tell you, point you in the direction of where there might be issues. It also serves the purpose, I should mention though, of when you've done that, you've done due diligence, you follow the best practices that we've described in the 2 previous practices, and you've done the pre-bal that Jason Link suggests, and it all helps when you present the model. So when you write it up for publication, that you've taken those steps helps a little bit get it through the reviewers actually, because it means that you have used common sense and common procedures, best practices in defining it. So being aware of that is worth the effort. What pre-bal does is it puts up graphs. You'll find it in Ecopath output pre-bal. Kind of, again, pre-bal, post-bal, because this is how you examine the model once you balanced it. There are these general things in there. It's fairly simple, but it may point you to why does this group stick up the way it does. Why is the QB for this group, which has a very low trophic level, that high? There may be good explanations for it, but it could also be there's a problem with the estimate. Like the production consumption ratio, we would expect that if you are low trophic levels, you're probably a smaller organism, and therefore you should have a higher production consumption ratio than if you are a big predator. What's required is common ecological sense. That's what you need. You need to have an idea about how things relate to each other. And you get that from looking at models, looking at the data in there, including balancing the model when it doesn't balance. So that's where I want to go now for the last half hour. What I plan to do now is to go to tutorial 2. If you look at the website, you can find a very brief text that basically tells you that the Anchovy Bay model that you get very used to if you follow this course, that model, I've taken it and I made, I think, 5 versions of it that don't balance. And the challenge is to figure out how to balance it, and because it takes you through the steps that are involved, and that's what I want to show you now. Ah, cute. That's Jerome Steenbeck. Locals are important. If anyone doesn't know what's important, then this should tell you that locals are definitely important. So here we are. We have Ecopath, and we are opening it. I'm going to start and see if I have anything up here. Oh, I've got something here. I'll just open Andrew Bay first. Basic input. I have a sense that this is really, really small. Is that correct? Yeah, that means I should go like this. Give me a second here. I think this is better. Hopefully you can see it now. So, basic input. So here we have the various groups that you're looking at. One thing you notice is these yellow lines here. They basically means that we have defined pedigree. So they're giving us an idea about the pedigree even from this screen here, which is pretty nice, neat, because you're more likely to change the things with low pedigree than the ones with higher. When you're getting used to your data and what's in there and in your model, this is an important aspect of it. Generally, what you do when you have a model is you go get your input in here, you get your basic inputs, you get your diet compositions in, and then you go to basic estimates to see it. Your balanced, your output parameters may be balanced model. Here on these screens, you can see the background is gray. That's because you will, in the beginning, you'll be confused about, are you on input or are you on estimates? So just that color coding is just to tell you, oh, you're on estimates now. And the blue ones here are the ones that Ecopath had estimated. So in this model here, it's estimated the ecotrophic efficiency for most groups, but not for benthos, which is a catch-all groups in this simple model here, ecosystem here, where we have assumed that 60% of the production is accounted for in the model. So we only account, we have 40% other mortality, and based on that, it estimates a biomass at 32 ton per square kilometer. And when you look at these numbers here, ton per square kilometer, what is 0.8 ton per square kilometer of shrimp? How do you relate to that? It's, well, you can see it's 10 times more than the whale biomass. And you know what? Making that kind of connections in your head is actually really useful for getting that ecological knowledge I mentioned to you a few minutes ago is the key, key knowledge. It's not the right word for it. I can't find the right word. It's what you really need is that ecological knowledge. That's what I'm trying to say, and you get that by looking at things like that. And helping you here is units. Units are really important. So they are mentioned up there on the top if they have units. Ton per square kilometer. Now, if we'd been a small group, I would have challenged you now to convert that into gram per square meter. And in doing so, you'll find that the conversion factor from gram to ton is 10 to the 6th, 1,000 times 1,000. And from meter squared to square kilometer is 1,000 times 1,000. So ton per square kilometer is the same as gram per square meter. And that's important. because it helps you relate to it. Now you suddenly have it's 0.8 gram per square meter of shrimp. And you can picture a shrimp, picture a bottom somewhere, and think about how many shrimp do you see there and how much does a shrimp weigh, and is that a reasonable estimate? That is, I really find it useful to swap between gram per square meter if I'm thinking about small things, to ton per square kilometer when I'm talking about whales and fish populations. How many mackerel schools do I expect to find when I look out over a 1 square kilometer area? And if I look out over a whole bay, how many whales would we have in this bay, and how big is the bay? Do we have any at all? You know, that it helps to relate to those numbers. The P over B here, I mentioned earlier, unit is per year. If you invert that, you get biomass over production, you get a unit of year, you get average longevity. So for whales, 0.05 inverted means 20. So the average whale lived for 20 years. That's, yeah. The average seal inverted, 6 years or so. Yeah, that's reasonable. Cod, 3 years, 1 over 0.3. It's not a very high fishing pressure. Nowadays, many places fishing pressure is higher, so it might even be a bit less than 3 years, which would mean PB higher than 0.31. And you can relate to those measures when you start thinking about it that way, and that is really important. Phytoplankton, here it has 240 in my model. Many other versions of this, many other versions of the Ancho Bay actually uses 120 and then 18 here. But then numbers again, if you think back to biology classes, phytoplankton we learned can divide about once a day under good conditions. That translates into 365 times a year if it's 1 per day, but under good conditions, so it doesn't always happen. So something down in the range of 100, 150, 200 is actually much more reasonable. Zooplankton, 35, yeah, that's small zooplankton. Talking right away that we're talking about something like Acacia, 1 or 2 millimeter when they have this. We have these expectations when you start looking at it, when you start getting more of these numbers. What you need is, that's what I'm trying to illustrate, to get a grasp of this, what you need is a broad understanding of the various components in the ecosystem, not a deep one about this species in this ecosystem in my bay right now, and all the that's not the required knowledge. It's the broad ecological knowledge, and that relates to also how these what they mean, what you see here, and how they relate to each other that way there. So zooplankton, production biomass ratio of 35 means it's a small one, 1 to 2 millimeter, like Acacia tonsa. The bigger one, like the big Calanus philmachicus that we see up in the boil waters, we're talking about more like 7 for those as a turnover rate. And they can live for several years. So average longevity doesn't mean they only live for, in this case here, for a few months. No, it's the average that we're talking about. So these numbers mean something. And the next thing here is not consumption, but production-consumption ratio over here. You remember the Ecopath mass balance once? I think you have heard about it before. Consumption equals production plus respiration plus unassimilated food. Now, in that equation, the unassimilated part for fish is based on work by a Russian called Ivlev. He measured a lot of these things in the lab, and generally 10 to 20 to 30%, 10 to 30% is the range for fish species. That means if you're big fish, slower growing, it's more likely to be down in the 10% range. If you're a small fish, fast growing, it's more likely to be up in the 30% range. It also matters how good food you get. So you can use these 10 to 30%, you can use that as a rule. The exception would be things that eat really poor food, like zooplankton eating phytoplankton is not very good food. It's all the shells and all of that. So that tends to excrete more. But generally 10 to 30%. So if you look at that, for whales and seals, it's lower. Yeah, their respiration is much bigger and their productive output is much smaller. So they have low production biomass ratio and high consumption biomass ratio. That's fine. You even heard about that in this video. Cod 0.12 and up. See, these are generally on the low side, what you see here, especially for anchovy. With 0.13, that's on the low side. I would think anchovy would be more in the 20-25% range. So these numbers mean something, and you have to think about them. You have to go down like I'm doing now and look at what they mean. Also look at ecotroph efficiency. Do they look reasonable? For phytoplankton, it's 0.88. So that means we have demand for almost everything, all the phytoplankton, which boils down to clear water. Do we have clear water in an anchovy bay? That's where you need to go and ask people who knows the bay well, and they will tell you. Well, if you have a lot of seasonal production with blooms, this is probably a bit too high. So generally we have that kind of things going into it. For anchovy, 0.95, 191, yeah, no, we would expect a high demand on anchovy, so that's quite okay. Had that been 0.1 for anchovy, we would have said, I don't like that. Why doesn't the model explain what happens to it? Of course, if you constructed a model that focused on something else and you didn't care about it, and you didn't have the things that eat it, and you don't have the fishery in it, then it might be okay. They might still be doing what they do, but you wouldn't explain what happened to them in such a model. So it depends on the question, whether it's acceptable or not. You have to be in charge of that. You have to evaluate that. The model can't do it for you. So that's why it's important you get into this thinking that we're talking about now. Yeah. There are lots of other things over here. Explore all of this. You can go in here. You can find lots of tools and flow diagrams that shows you how them. Oh, you can't even see them at this screen resolution here, but there's lots of things you can do with this, and we can take it much further. We just can't do it right now. So let's try another model. Santiago, are you listening?
I am
Can
here.
you give me a number between 1 and 5?
It's
A random number between 1 and 5.
4.
4. Ecopath mass balance number 4. Do you want to shape these? Yeah, I can shape that. That doesn't matter. So this is one of the 5 unbalanced model. So we have now a version here of the anchovy bay model. And we have all the input data, we have basic input, we have diet compositions. So now we're going to balance the model with basic estimates. It balances just fine. That's interesting. So what's the issue here? We have our model, we're done. Maybe I should examine it a little bit closer, what's here. First thing I see is phytoplankton biomass is 45. I multiply that with 120. That gives me something around 5,500 or something like that. Okay, so the primary production is 5,500 ton per square kilometer. Now, I don't know much, but I used to work in the North Sea, and that's one of the measures I keep in my head, is the primary production in the North Sea is about 3,500 ton per square kilometer. Is Anchovy Bay more productive than North Sea? North Sea is a shallow area with high productivity. There's a lot of fishery there. No, it's not. Something is wrong here. Anchovy Bay cannot be more productive than North Sea. You know, this is the only estimate I remember is the North Sea. I don't know anyone else. I know 3,500 for North Sea. That's all I need, one reference point. And I can then relate, knowing that system, I can relate when I see another system to where would it be on that axis. I would expect Peru to be higher, as an example. You know, so that's what I'd be looking for. That's my 1 point. That's all I need, 1 point. Then I can relate to that number. In this case here, see what is happening here, it's been estimated, it's blue. Actually, they've all been estimated. That tells me if there is an issue with this thing down in the bottom, I have to look at all the way through the system, and I get up here. 0.8 ton per square kilometer of whales. That is 800 kilogram per square kilometer. Can you imagine looking out over a big bay, and you see, for every few square kilometers, you see a whale? So in this case here, it's conversion error that's behind that. The original number here, if you look at your model, was 0.08. So that's a very simple, very easy to do area. It could be in the tutorial one that you forgot that's 100 square kilometer, and you calculate things. You forgot to divide by 100 to get per square kilometer. That's how you get that kind of error. And they show up, and when you fix them, oh, now the EE is invalid for whales. So maybe it wasn't an order of 10. I made a mistake here. I went too far. Now ecotrophic efficiency for that group is 4. When you have that kind of problem, you go in and you go to mortalities. This is the first place I normally go. I normally don't even go here. If there's any issue, I tend not even to look here. I go straight to mortalities, and I look for what's causing it. Oh, this is getting weird. Oh, I think our biomass is too low now, because the biomass accumulation rate is 0.2. See, POB is 0.05, but biomass accumulation rate is entered here as 0.2, so bigger. So if you look up at the top here, see a really neat thing. This is the second master equation of Ecopath. Production of biomass equals fish mortality rate plus predation mortality plus biomass accumulation plus net migration plus other mortality. It's an equation that's here, second master equation. So 0.05 plus 0.2, then we estimate this one has to be minus 0.15, which is not possible. So there's a problem with this. That's what I look for. And we could go in and we could fix that, but we only have 6 minutes left. I talked way too much. So I'll just show you one more. You can take a random one here. No saving. Next one. Looks different. We go to Ecopath output. We can take basic estimates. Oh, cod and whiting are not balanced. EE is bigger than 1. So what we do now is we notice which one it is. We can also get that, you can't see the last pure screen resolution here. We can also get that down from status down there. But now we know cod and whiting EE is too high. We go mortality rates, and then we check, is it fishing or is it predation? So we look at these two especially. For cod and whiting, it looks like it's, whiting, look at that huge predation rate there, 0.6 is bigger than the PB. So obviously there's too much predation on this group. 0.6 is just higher than 0.5. So the next thing we do is we go to predation mortality rate, and we look across for whiting here. Oh, we see it's caused by, oh, several groups eat too much. Now, how can that, so it seems to be several. It's not very often we get in here, you see the squid showing up or something like that that has, ooh, it's one number. It tells you right away what predator to go for. Here it's more like that seals are really important. Seals are more important than cod and whiting, really. These are two big fiscivores. How come seal is that big? That seems strange. So this is what you get out. I always, when I look at a model, go in and I do this, a big model, click here where the number is, and I look across and I look for who are the common predators, who are the important predators. And sometimes you go in and you look across here and you say, for anchovy, whiting is really important. Yeah, that they eat, and mackerel is really important. Yeah, that makes sense. That's okay. I expect that, and the other ones contribute less. So sometimes it makes sense, and when it does that, you store that as your ecological knowledge. Other times it screams at you, seals, the most important predators on whiting? Maybe not. And you go back there and you figure out, oh, seals there was a remark up there. We did that before Excel, actually. Had to brag of something, was 0.0609. So this one has been increased with an order of magnitude. That's where the issue is on this model here. This number here should have been 0.0609. What it does, that big number, if we go back, is that it just blows up the predation for that group on cod and whiting.